We saw that Heisenberg group competes with the Euclidean space in terms of the richness of the structures we can put on them. They are metric spaces, they have a smooth structure, there is a group action on them, which makes them a Lie group, and there is this notion of dilation, which I have been advertising that is quite important for development of calculus on them. That topic coming up very soon, but we have to first understand the very basic simple maps on Heisenberg group H1. In this lecture, we want to see what deserves to be called linear maps of the Heisenberg group. First of all, I must emphasize that linear maps are the backbone of analysis and calculus. The very definition of derivative relies on the possibility that locally a function resembles a linear map, and that linear map becomes its derivative. Then we use this linear map to define Jacobian determinant at a point, and we use that to in the formulation and proof of change of variables formula, area formula, coarea formula, depending on the dimension and codimension. The derivative of a map between two manifolds is a linear map between their respective tangent spaces, and so on. So you can see the importance of linear maps in analysis. What deserves to be called a linear map on Heisenberg group would be a map that respects the multiplication. That makes it a group homomorphism. And then it respects dilation. So if you have a point in Heisenberg group P and you dilate by R positive, then this requires that you can first apply function to P and then dilate the resulting point. Let's begin by some basic observations. Let f of 1, 0, 1 be the vector x1, y1, and t1. And similarly, let f of 0, 1, and 0 be equal to x2, y2, and t2. I intentionally don't talk about the third one because I will recover it from these two. But the first claim I want to prove is that t1 and t2 in this case actually have to be 0. Why? Well, pictorially, here's the reason. If you are at the origin and you map, so let's say this is f of 0, 1, 0, 0. If it's off the plane, what happens is when I dilate, on the one hand, by homogeneity, I must remain on this straight line. On the other hand, by dilation, the third one dilates like a square. Therefore, it's a parabola shape, and then there is this gap appearing here, contradiction, which shows that f of 1, 0, 1 could not be off the xy plane. That's the whole idea, and I'm gonna now put it in precise algebra. Pick r in the integers, then well, r 0, 0 will be a certain number of summations of, actually not summation, just group multiplication, because we're multiplying the same value. There won't be a twist, so this will be just the Euclidean multiplication, which is addition of these, so r many times. And from this we will have that f of r, so from homomorphism property here, we will have that f of r 0 and 0 is f of these multiplied r many times, and this will be x1, y1, t1 multiplied into itself r many times. And again, if same vector multiplies into itself, it becomes just group Euclidean addition. So this becomes r times x1, r times y1, and r times t1. But there is another thing. On the other hand, r0 and 0 is group dilation by delta r of 1, 0, and 1. So, by being homogeneous, we see that f of r 0, 0 should be the group dilation of f of 1, 0, 0. So, typo here, sorry. And that would be, by definition of dilation, this would be rx1, ry1, and then r to the power 2, t1. So because my function f is simultaneously homomorphism and homogeneous, this forces that the third components be equal. So rt1 should be equal to r squared t1 for every r in natural numbers. And this forces that t1 be 0. So similarly, so proof of t2 equal to 0 is the same. The first observation is that f of horizontal vectors, basically I and j vector, should remain in the plane. Let f of 1, 0, 0 just be x1 and y1 and 0. And let f of 0, 1, 0 be x2, y2, and 0. Claim. And explanation of why I'm not checking the third component. F of 0, 0, and 1 must be 0, 0, and determinant of this thing. So x1, y1, x2, y2. If you multiply 1, 0, 0 into 0, 1, and 0, you will get, if you follow the group multiplication, this will be minus 2. From this, we see that f of 1, 1 minus 2 will be multiplication f of these two, so that will be x1, y1, 0 dot x2, y2, and 0, add y1, the first two, so x2, y1 plus y2, and then here you will have minus 2 times x1, y2 minus x2, y1. Notice that 0, 0, and 4 is equal to 1, 1, 2 times the inverse of 1, 1, negative 2. Then f of 0, 0, 1 is f of dilation by 1/2 of 0, 0, 4, and therefore by being homogeneous, that becomes dilation of the image, and that exactly gives you x1, y2 minus x2, y1, and that's the end of the proof, because this is exactly determinant of x1, y1, x2,